Good morning, guys. Here's our challenge problem for the day. Essentially, we're investigating the concept of moving a block up an incline using a horizontal force. So hopefully this problem will help you out. Here's our problem description. We have a 6 kilogram box sitting on a ramp that's inclined at 37 degrees above the horizontal. We're given the coefficient of kinetic friction between the box and the ramp. That's this 0.3 number. And we need to solve for what horizontal force is required to move this box up the incline with a constant acceleration of this 4.20 meter per second squared value. And if you draw a picture of the problem, and this is really it, we have our box sitting on the ramp, we've labeled the mass and the angle. One thing I would recommend is labeling the x-axis parallel to the ramp like this, and the y-axis perpendicular to the ramp like that. You can choose to do it differently, however it may be a little more involved, so just a heads up, as we saw in, I think it was the Advanced Newton's Laws problem number 1. So if you get stuck, there's a reference. The next thing I would consider drawing is the acceleration that was provided off to the side. That's the 4.20 number. And then don't forget, we're solving for this horizontal force being applied to the box. And so let's take this information and apply it to the free body diagram and see what we get. I'm going to take this coordinate axis up here and blow it up like this. So, forces acting on the box. Let's list them. We have the weight of the box, which pulls directly downward. The normal force of the ramp acting on the box in the plus y direction. We have the horizontal force that we're applying. And finally, we can't forget that there will be kinetic friction, and it will be acting in the direction opposite to the way that the net acceleration is moving. So that will be in the negative x direction. And I think that's it for our forces. The next thing we'll have to do is label the angles, and I'll go ahead and put them in next. You may be asking, how do we know that we can take the ramp angle and copy paste it in these two locations? One answer to that question is that these are similar triangles, but that's not a very satisfying explanation. So one thing I would ask you to imagine is extend this red F vector all the way out here as a parallel line to this gray dashed vector, right? So we would have a pair of parallel lines, F and the dashed gray one, and then we would have an intersecting line between two parallel lines, essentially the x-axis. I've drawn this up here as a reminder in the top right corner. And so that means we can copy paste this angle here into this location because these are corresponding angles between parallel lines. That's the justification for this angle here. The justification for this angle is a bit more involved, and I don't want to spend too much time on it because it's more geometry than it is physics, but if we recreate our free body diagram here over to the side using 3 separate triangles, as you can see here, I've got one with the right angle here, I've got 2, an upside down one, with the right angle drawn as a light brown color, which we'll come back to later. And then an even smaller right triangle here with the right angle in black. So I've taken the free body diagram here, put it off to the side, and I've extended these lines out and drawn 3 separate triangles. And the idea is that I want to prove that the angle here, we'll call it alpha because we don't know what it is. Maybe it is theta, maybe it could be something else. We want to show that it is indeed theta. We want to show that this is the reason why we can take this angle and put it here. So the reasoning goes something like this. The angle ABC, which I've labeled as the right angle, B here, that's the sum of two smaller angles, ABD and CBD, which I've also labeled as beta and alpha. So take a look at this smaller angle here, or this smaller triangle, forgive me. We have the sum of these three angles in this smaller triangle being theta, beta, and 90 degrees. That's 180. If I subtract the right angle off from this triangle, I get beta plus theta is equal to 90. So I have a right angle here equal to beta plus alpha, and then I also have theta plus beta equal to 90. So we got two separate equations here. So then if we have beta plus theta is equal to 90 degrees, and beta plus alpha is equal to 90 degrees, we can set these two expressions equal to each other, subtract beta from both sides, and show, hey, angle alpha is indeed theta. There is indeed a justification for us being able to take this angle and putting it here. It's because it can't be any other angle due to the geometry of the situation at hand. But since this is a physics problem and not a geometry problem, we don't need this to answer the problem. This is just a interesting aside if you would like to know why we're able to put those angles in those locations that we do. Anyway, moving on. The next step is to break our vectors into the appropriate components. And the first one I'm going to do is the weight vector. I have the cosine, the adjacent side here, and the opposite side here. And similarly, over with the force vector here, F, I've got F cosine as the adjacent side, and F sine as the opposite, pardon me. And I've also included both right angles. And that is everything that we need for the free body diagram. Right? This is the entire thing. And so let's use this as a reference to set up Newton's second law and then solve for what the magnitude of F is. And so I'll set this whole spiel aside and grab the old tool off the tool belt, F equals ma. We'll start in the x direction. And so we're looking for the sum of forces that are directed along this oblique angle, right? So we have F cosine theta pointing up and to the right, so it's positive, and then we have W sine theta pointing in the opposite direction, as well as the kinetic friction, so those are the negative terms here. And that is equal to the mass of the box times the acceleration in the x direction, which we have from the problem description. We'll come back to that later and fill that out. In the meantime, let's exchange this expression for mu sub kn. That is what we know the expression is for the kinetic friction of an object. We can't go any further because we don't have an expression for the normal force. So let's switch gears and move over to the y component. We have the normal force pointing in the positive y direction, and we have W cosine theta pointing in the opposite direction, as well as F sine theta also pointing in that direction. So those are the negative terms over here. There is no net acceleration in the y direction because as the box moves along the ramp, it doesn't go up or down perpendicular to the ramp. If it did, it would be floating in the air, or it would be inside the ramp. It doesn't do that. It stays along y is equal to 0. The entire time it moves along x and goes up and to the right. So that means we can take these terms here and move them to the other side. So now we have an expression for the normal force. The next step is to take what I've underlined in blue here, the expression for the normal, and plug it in over here. Don't forget, we have the 4.20 meter per second squared value we can plug in here as well. And then we'll use all of that info to solve for f. So let's do that on a fresh page, and we'll start from this expression right here. We will exchange the normal force for the one that we got from the sum of forces in the y direction, which is this one. And our next step is to distribute the coefficient of kinetic friction now to what's inside the parentheses, and that will look like this. Remember, we want to solve for f, and that means we need to isolate all the f terms on one side. So I'm going to put this term that has f in it, and this term that has f in it on the left, and everything else is junk that gets lobbed to the other side, as you'll see here. And I will take f and factor it out from both of these terms, which will look like this. And now we can divide both sides of the expression here by what's inside the parentheses, this cosine theta minus mu sub k sine theta. So now I have an expression for f, and if you really want to be a pro, you can go one step further and factor out one more thing, because we know that the weight is equal to mg, so we have m, and every single term in the numerator here. So the final simplification or simplified form of f, will look like this. And we have every single value here, despite how messy it looks. We were told that the mass is 6 kilograms. We were told that the acceleration in the x direction is 4.2. We know what g is. We know what theta is. That's the 37 degrees. We were told what the coefficient of kinetic friction is. That's 0.3. So we have everything now. If you plug that all in, here's what that looks like. And answering the problem to 3 significant figures will give you this value, 121 newtons. That is the value of f. That is the magnitude of the horizontal force required to accelerate this box along the ramp in the positive direction at 4.20 meters per second squared. Thanks for watching.